Now we're going to walk through pretty much the identical problem describing the position, velocity, and acceleration of a particle freely moving about in a 2D plane. The only difference is the quantities that we use to describe the position vector are going to be slightly different. So I'm just going to set this problem up the exact same way we did in the last video. We have a particle moving around. It's located at point P. And we are going to define its motion with respect to a reference frame, frame A, which is defined by an origin point O and two perpendicular unit vectors A1 and A2. And our position vector, which is going to describe the location of point P in frame A with respect to the origin point O, is drawn as such. So now we have the position vector pointing from point O to point P. It's a little off. We'll just make this point a little bigger. Now to express this position vector mathematically, ROP, we need to define the magnitude of the vector in each of these two directions, A1 and A2. So in the last video, you saw that we broke down the two components of this position vector, one component in the A1 direction, one in the A2 direction. And we described the magnitude of these components as X and Y. And we just assumed that we knew those quantities. In this example, we are going to assume that instead of knowing X and Y, we know we know R, which is the length of this vector here, and we know theta, which is the angle or direction of that vector. And so that means instead of being able to write simply X or Y, we have to now write the magnitude of each of these components using the variables R and theta. So it's actually not that difficult. We can write the magnitude of this component in the A1 direction as R cosine theta, and we can write the magnitude of this component in the A2 direction as R sine theta. And thus, when we actually write out this vector, we say that ROP is equal to R cosine theta A1 plus R sine theta A2. Pretty straightforward. So now we're going to do the same thing. We're just going to go through the same math in order to get the velocity of point P in frame A. And so we're going to take the time derivative of our position vector, which in frame A, which written out looks like this. All right, so let's focus on now taking the derivative, the time derivative of this first term here. So again, we're going to use the product rule. The only difference is that now instead of having two products like we did in the last product of two terms, in the last example, we now have a product of three terms. So to calculate that derivative, we use the product rule, which is going to look like this. So a little bit more involved. So to start, we are going to take the derivative of r times cosine of theta times a1. And now we have our second term, which is r. And now we have to take the time derivative of cosine of theta. And this is now where we need to use another calculus rule, which is the chain rule. And the chain rule, if you remember, says that if you are taking the time derivative or the derivative of a function inside of another function, that is equal to the derivative of that inside function, which in this case is g, we'll call it g prime of x, times the derivative of the outer function. And so if this is unclear to you at all, just Google chain rule or ask me about it and I'll go over it in lecture. Okay, so we need to use the chain rule here. We have, in order to take the derivative of cosine theta. So we'll start by taking the derivative of the inside function. So theta is a function of time, so we have to take that derivative as theta dot. And then the derivative, so that was the derivative, oops. Let me write this out here. So that was the derivative of this portion. And now we need to write the derivative of this outside function. Can't really see those colors. This outside function here. And so that is negative. So I'm just going to turn this into a negative sign and then sine theta times a1. And then the last term from our product rule is r cosine theta a1 dot. All right, so these are the three terms that result from taking the time derivative of this first term here. So now we do the exact same thing for this second portion here. So that's going to be r dot sine theta a2. Again, we need to use the chain rule, so we're going to put r theta dot cosine of theta a2 plus r sine of theta a2. And this is all for the velocity. Now again, just like in the last problem, we're going to assume that frame A is fixed, meaning it doesn't move around in this plane, it's static. And so with that, we can take these two terms and set them to 0 because A1, the vector A1 and the vector A2, these unit vectors do not change. And with that, I can then nicely clean up this, these terms and combine terms and get the following. So I have the time derivative of r cosine theta minus r theta dot sine theta a1 plus r dot sine theta, that should be a plus, plus r theta dot cosine theta a2. And so when we define the position vector using the terms r and theta, the velocity vector looks as follows. Okay, so now that I've cleared the space a little bit and rewrote the position vector and the velocity vector again up top, I'm going to go through and calculate the acceleration of point P in frame A. The process, as in the fact that I simply need to calculate the time derivative of the velocity vector, is obviously the same as what we did in the prior example. The only difference is that taking this derivative requires a bit more algebra than we needed in the prior video. Okay, so I'm going to write this out here, that we're taking the time derivative of this big chunk. So bear with me as I write this out. All right, just made it to the end. Okay, so now we're going to go through and actually take the derivatives of these individual terms. So we're going to start with this one here. So I'll put this, and I'll write it in different colors just so that it's a little bit clearer for you to follow along. All right, so we're going to use the product rule here as well as chain rule again. So we have the derivative of r dot is r double dot. I'm going to multiply that by cosine theta. And now we use the chain rule, and we will get r dot theta dot sine of theta. And now we're going to move over to this next term, which again we're going to use a combination of the product rule and chain rule. So we'll start with the first term. So we have minus r dot theta dot sine theta. And then we need to take the derivative of that second term. So we have r theta double dot sine theta. And then here's where we use the product rule. So we have minus r, this will become theta dot squared times the cosine of theta. And that's all for A1 plus, oh, running out of colors here. So we'll take the derivative of this term, and that is r double dot sine theta plus we have r dot, again, theta dot cosine of theta from the chain rule. And let's see, what other colors do we have? I'll go purple for the last one. And so our last derivatives are, we have another r dot theta dot cosine of theta plus r theta double dot cosine of theta plus, oh, actually that's going to end up being a minus, minus r theta squared theta dot squared sine theta. So as you can see, that's quite a long one. Of course, you should immediately be able to recognize that there are some terms that can be combined. For example, these here. So we can simplify a little bit, but even with simplification, still quite long. So we'll call this cosine theta, and now we just put 2 sine theta. Nope, that's a cosine. And then we'll simplify this next term here. Okay, and so with that, we now also have the acceleration of point P in frame A, and that's in addition to the position and the velocity vectors that we derived in the process.